Hey, welcome back. Kind of a dreary morning for us out there, it looks like, on this Thursday. Um, we transition a little today. So today we go from refraction, basically bending light, into reflection. Now, reflection is one of those things that you probably know an extensive amount about, meaning from your everyday use of mirrors on cars, of bathroom mirrors, of stuff like that, right? Um, so I'm going to try and put a little physics blend onto that just so that you can see those real experiences from a scientific kind of viewpoint, so to speak. Okay. So today what we're going to do is we're just going to talk about general reflection, and then we're going to talk about images formed in flat mirrors. All right. Like the picture, very tranquil spot, right? Probably pretty nice, quiet. If you're into kind of serene places like that are nice and kind of chilled out, so to speak, then that's a good spot. All right, here we go. So when we've been drawing light rays for the last bit here, right? We asked the question: how have we been diagramming light beams? Well, with arrows, right? So anytime that we've drawn these, we've drawn arrows, right? When we drew with the convex mirrors, we drew arrows, right? Even whether it was on a Google Doc, whether it was on a piece of paper or something like that, it had an arrowhead on one end of it to draw and indicate directionality for us, right? If we look at just a straight up light bulb, that thing pops on, turns on, right? We're going to see light coming out in all 360 degrees, all directions, all that, all three dimensions, right? So um, that's what we end up seeing is that this light does travel in a straight line for us, and we diagram that as an arrow. Okay. Um, so I want you to think of just a single beam because if we look at a light bulb, we get all kinds of light beams, right? So I want you to think of it as like it's a laser, right? Um, so what you're going to see is like my green laser that I used a while ago. We're gonna bounce it off a shiny flat surface. Let's say like a mirror, a CD. It could be water. It could be metal. We asked, what do you think the angle of the incoming beam compares to the angle of a reflected beam? Well, if we look at it, we should see, what do you think? Should look like it comes in at a pretty similar angle as it goes out, right? When we measure these incoming and outgoing angles, the angles are measured with respect to a line that is the normal to the surface of the mirror, all right? So some terms for you: angle at incidence, angle of reflection, and the normal. So if we have a reflecting surface, what we see is that normal is always perpendicular to that surface. So if that is a completely flat surface, it's going to be perfectly perpendicular to it. If it's angled, it's still perpendicular. If we put it on like a ramp like we did way back when, it's still going to be perpendicular to that thing. Okay. Angle in is that angle of incidence. Notice how that angle is going to be the same as the angle going out. So what we end up seeing is the angle of incident is equal to the angle of reflection, right? And again, it's based on where that normal is. Whatever angle you put into it is going to be the same as that angle you get out of it. All right. It is the law that the incident angle is the same as the reflected angle. Okay, so the ingoing and outgoing should be the same. If we were to, if I were to grab my, sorry, I want to grab my. If I were to try and grab, a slide tool here or something like that, what you're going to see is that right along here, let me see if I can get this here. Annotate. Let's get some color. Let's get some of this. So right along here, that'd be where our normal would be for us. Okay? Meaning that that would be a dashed line. This angle here is going to be the same as that angle there. Okay? So that's what we end up seeing. That's how that ends up really working out nice for us. Okay? So, got a pencil, right? And we got what we call the eye of physics, right? I have to say it with a real loud, bold voice, the eye of physics, right? So what we see here is that if we look at this flat mirror here, what we're going to see then is that when the eye of physics sees a reflection off the bottom, it's looking at about the midpoint of the mirror. Again, we see that should have right? A normal right smack dab in the middle, all right? So that's what the light beam actually does. Now, what our eye perceives is that it actually comes from the backside of the mirror. Now, I don't know if you've ever seen, like a mirror, kind of the construction of it or how they make it, or even the back part of the mirror, but um, you can't see through normal like bathroom mirrors. They basically put some silver nitrate on it. It forms up a real flat, nice surface, and then the backing becomes opaque, so you can't see through it, right? So we perceive that that image is coming from behind it, all right? So if we look at where it's just sharpened, right? Again, we're going to look at a different angle for it, and we perceive that it's back there. If we look at the top part, the graphite part of the pencil, we're going to see and perceive that it comes from back there. So what ends up happening is that we perceive through this mirror that we're actually looking through the mirror to that wall, inside that wall on the other side of the mirror. That's where we're seeing our image, right? And right, little trick for you. When you're in your mirror your next time, think about this, right? I want to touch my left ear. Well, I take my left hand, touch my left ear, but on the mirror, which one are they touching with? Ooh, they're touching with the right. They're touching with the opposite, right? That reflection, that image on the back edge of the mirror for us, or behind the mirror, is really what we start to see. Okay, try this out. Draw me a stick human. Doesn't have to be perfect, right? You've seen mine. Give him a name, or her name if you like. Draw a flat mirror in front of them, and make a ray diagram showing light rays coming from the human's feet, the top of the head, and the belly button, all reflecting, all ending up at the human's eyes. Keeping in mind that the incident and reflected angles are the same, right? Now, or you can just go back to the last time you stood in front of that mirror. Think about, where do your eyes have to be in order to see the top of your head, right? Where do your eyes have to point in order to see your belly button? Where do your eyes have to point in order to see your feet? Okay? And think about those angles that you're creating in order to try and see those different body parts, right? So, here's mine. I'm going to name mine Ray. Oh, such a science joke. I'm sorry. I love it. So that's our mirror. That's our height. We see there's our normal. So for Ray to look at his feet, he's going to look at about the midpoint of the mirror, right? And again, as you've grown older, this has become more of an obvious statement for us, because we're able to say, well, I can't look at the bottom of the mirror because that's going to look at the carpeting or the floor or whatever I have there, right? So I have to look at that midpoint there in order to see my feet, right? To see my belly button, I'm looking at the halfway point in between my belly button and my head, right? Again, a normal is put in there just to show the angle of incident is going to equal my angle of reflection. To look at the top, right, I'm going to have to look up just a little bit, right, just to see that. And that normal is still going to be there, all right? So we want to know, where do the light rays originate from? Well, they originated from back here, right? Meaning that that's what it appears for us, that we see this other version of Ray, right? And it's a backward version of Ray, so to speak, for us, okay? That's where it appears. That's where our mind's eye is saying, oh, it's right. I can see the back, through the wall. I'm looking through a glass pane, and they are just a pure reflection of me in that other side of that mirror, all right? I'm sorry, that's a little trippy, isn't it? It's kind of deep, I know. So we get this concept of magnification. Write it down. We'll use it later. We're not going to use it right now, all right? So that's h prime, the height of the image, over h, just the height of the object. Now, if any of you have some of those bathroom mirrors, like the face mirrors, my wife has one. I tried shaving with it one time because my mirror was all fogged up. I tried using this mirror, and it was like the most humbling thing I've ever done, because, oh my God, it magnified my face so much, and I'm like, oh man, look at all these gray hairs in my beard. Holy man. and and it's just like, oh, why do people use those things? They just, ooh, man, it showed off some stuff in my face. I was like, whoa, there's a lot of gray there. And oh man, yuck. So that would be one that would magnify it large, right? And you can also see in your car mirrors on your side window, right? Objects may be closer than they appear, right? That's that magnification piece. So how big do we see it? How small is it? How far away is it? All that sort of stuff also comes into play for us, right? Yeah, I hope you folks do know what side mirrors are, right? Sometimes driving around Lakeville, it appears like some don't, but that's other people's kids, right? Yeah, for sure. All right. Here again, if we just look at this image here and we see this thing, P and Q, that's still our object distance is P. Our Q is our image distance, right? And we're not going to, please don't get overly caught up in trying to write down what P and what Q is and how far it actually is and how far it actually isn't and how high it. We'll talk through that stuff later. Okay. Today, I just want you to see that image formed on those. All right. So, like we talked about, okay, P is all about the object. H is all about the object. Q and H prime are all about the image. Okay. All right. And again, we can use these concepts later on to determine some stuff out of this. Okay. So then we ask the question, is the image real or virtual? Now, in order for it to be a real image, and I'll explain that in a second, so I'm not going to give that away just yet. I want to see what you think, just because I don't know that you've heard of real versus virtual images. In this case, this thing should be a virtual image. Okay? A real image is described as light actually passing through the image. All right? So when we looked at my optics bench, so the meter stick with the candle, with the lens, with the paper. That was a real image. The reason that was a real image was because the light actually did pass through that image. Okay? A virtual image, light does not actually pass through that image, but appears to diverge from that image. So for us, when we look in that mirror, that's a virtual image. When we drew with the concaves, the ones that were fat on the top and skinny in the middle, right? Those, when we saw the image on the same side as the object, those were virtual images. Light did not actually pass through there. That light actually went out and spread out and went away from us. All right. So, so just think about, can that light in a flat mirror actually get to that back image? If it can't, then guess what? It's a virtual image. All right. And what that means to us is that it's the light just can't get there, and that's why it's virtual for us. Okay. Is it ever possible for it to pass through? No. We can't get a real image out of a flat mirror, right? Because that would mean that this thing would have to form on the left side. That's where it would have to form. Our image would have to form right there, which we don't get. Our image appears to be in the mirror on the other side of the mirror. Because it appears to be there, that's why we call that thing a virtual image, right? So flat mirrors will always produce virtual images, okay? All right, your quiz tomorrow. You're going to have to do a thin lens equation problem. You're going to have to just talk about the thin lens lab a little bit, or answer questions off of that, I'm sorry. Kind of what happened, what we saw with that. You're going to have to answer questions about angle of incident and angle of reflection, just to see how those work. And then we're going to talk about just images formed in a flat mirror. That'll probably be about 10 questions. You'll probably get 1 or 2 thin lens problems, right? So those will be about a total of 2 pointers or something like that. So, all right. Otherwise, today, I don't have any homework for you. All right. Listen to the lecture. I'll probably put a couple videos up online about reflection and maybe some crash course or some science stuff up, sciencey videos up there that you can see. Otherwise, quiz will be available tomorrow at 8 a.m. It'll be open until Sunday at 11:59 again p.m. All right. Make sure you get up. Make sure you take it. Don't forget this time, please. Otherwise, I won't see you. So have an absolutely fabulous weekend and take care of yourself and be safe. All right. Hope to see you folks soon. Honestly.